Hi, everybody. We're here to talk about the normal curve. This is the most iconic distribution in all of applied statistics, historically in statistics and data science, and so forth. Um, so you have the function there. That is the actual function, the bell curve. The bell curve, right? The normal distribution is right there. And we have mean and mu and sigma, right, are the mean and standard deviation. Those are lowercase Greek letters. And of course, we use this notation with a capital N and parentheses, mu comma sigma. That allows us a quick way to say, hey, this is a normal distribution with mean mu and sigma, the standard deviation of sigma. Okay, so why? Why is the normal distribution the big rock candy mountain of statistics? And it turns out that there are a lot of nice properties, and we use these properties and then apply these properties to other distributions, right? That each point on the x-axis represents a raw score in the distribution. Like if we're talking about ACT scores, right? Then each point on the x-axis is a raw score. And if you draw a vertical line through that raw score, there is a percentile, very specific percentile or p-value that can be calculated um, for that vertical line, that point on the x-axis. And you can reverse the process. If we know the percentile, then we can figure out the place on the x-axis where that corresponding score is. Okay, so this is actually extremely helpful to us. And here you see the bell curve actually split out in turn, and there are dotted lines there at the standard deviations, right? So the +1, +2, those dotted lines, those are 1 and 2 standard deviations above the mean. The mean is there at 0, the red line. Below the mean, you'll notice -1, -2, that is 1 and 2 standard deviations below the average. All right, so it turns out that there's this very helpful shape, and we know some things. We know from the empirical rule that about 68% of the scores in the distribution will lie within one standard deviation of the mean, and we know that 95% of all the scores will lie within two standard deviations of the mean. Sorry, that's supposed to be a 95. Right? And then we know that 99.7% of all scores are going to lie within three standard deviations of the mean. That's 99.7%. Okay. So, by the way, this is called the empirical rule. It's the Chebyshev theorem is a more generalized form of this, but this empirical rule allows us to know exactly where all the data are based on number of standard deviations away from the mean. Okay, so this is why standardized scores and standardized tests exist. Why? Because every single place on the x-axis corresponds to a raw score in the ACT or SAT or the IQ distribution, and then this percentile we can calculate. That's the area under the curve that's to the left of this vertical line. Okay, and also I can do the integral. Why? Because the area under the curve to the left of that vertical line is the p-value. That is the definition. So the the bell curve, right? This is where standardized tests come from. Why? Because each raw score corresponds to a vertical line. I can calculate the percentile ranking based on that. If I know the percentile I'm looking for, I can find and calculate the raw score. So that's why we have these standardized tests. That's what we'd like to demonstrate. And we'll do that in the rest of this PowerPoint presentation and in the notebook. Okay, so a z-score, a standardized score. So again, these standardized tests are related to standardized scores. And notice that we have a very simple formula. We take the score that we're finding a standardized score for. So like, let's say you made a 1350 on the SAT, right? So then you subtract off the average SAT score, subtract the average, and divide by the standard deviation. And that is your standardized score. And what will it measure? Your standardized score measures how many standard deviations above or below the mean you are, right? So positive z-scores mean you're above the mean. Negative z-scores mean you're below the mean, right? So if you have a z-score of 1.2, that means your score is 1.2 standard deviations above average. All right. And if you have a z-score of negative 2.3, that means your raw score is 2.3 standard deviations below average. So the z-score, the standardized score, just converts it into a standard deviations above or below average, right? And we often are stuck where we don't know the mean or the standard deviation. For example, say we're studying perfectionism scores at UNG Dahlonega. We have 7,000 students and they all would have a perfectionism score, but we don't know them. And we don't know what the overall population average or population standard deviation would be. So we can use the sample average, X bar, and the sample standard deviation, S. And we can calculate an estimated z-score based on that. Okay? So it's still a standardized score. We just don't have the exact values, mu and sigma, right, for the formula. So we can estimate it with these estimated values, right? We use X bar to estimate mu. And we use the sample standard deviation S to estimate sigma. And we can, at a pinch, use the estimated values to stand in for the real values. Okay, so how does this work? Okay, so generally speaking, the ACT has a bell-shaped distribution with average score 21 and a standard deviation of 5. Okay, so if Molly scores a 29 on the ACT, what is her percentile score? Okay. Well, the first thing we do is we're going to have to find the standardized score, right? So we take Molly's score of 29 minus the average of 21 divided by the standard deviation of 5. That's 8/5 or 1.6, okay? So far, so good. So now we have a standardized score of 1.6. We know that Molly's ACT score is 1.6 standard deviations above average. Okay, now we're going to use the p-norm function if we're in R. We can also use the statistical table. Okay, so these are linked, and let me pause the video for just a second and get these links so I can show you where these resources are. Okay, so this is my faculty webpage, and you'll notice the resources in yellow, and there's a 3350 prob stats resources tab, and let me get rid of these stray marks, right? And I can click on Z table. Now, this is going to be fairly large and hard to see, so I'm going to make it smaller, just so we can see it in the room that we have on this screen, right? And what am I looking at? Okay, so these are the Z scores down to the 10th place, and the hundredths digit is here. So if I want to look at z-score of 0.45, I have to go to the 0.05 column and the 0.4 row, right? So let me see if I can show that. Sorry that this keeps bouncing up, right? If I want to look at 0.45, I have to go to this column and the 0.4 row, and then the value where that intersection is 0.636736. Okay, so what am I trying to do? I'm looking for 1.60. There is no hundred, so I'm going to be in this first column here. So I can just scroll down. There it is, 1.6. Right, and I'm looking up this value in the 0 column because it came out even to 1.60, right? So I know that the p-value is 0.9452. Okay, that's really good. 0.9452 from the table, right? Or 94th percentile. By the way, we truncate percentiles, so even if it was 0.949, even though that rounds up to 0.95. With percentiles, you are never at the highest percentile until you're actually 0.95 something. That's when you get to the 95th percentile. So we don't round percentiles, we truncate. And I do understand that this would round up to the 90 to 95 if we were rounding that number 9452. But it is the 94th percentile. Okay, so we can reverse this. And what if we know that Molly scored in the 89th percentile on the ACT? What was her raw score? Well, again, traditionally speaking, we know what that distribution is. So what are we going to do? We're going to reverse the process, okay? So we're going to go in to the table, and what am I going to do? I'm going to try to find this 0.89 in the table and then find out what the standardized score is. When I have the standardized score, I can use the z-score formula to turn that around and solve, okay? So let's at least look at that process. Right, so now I'm looking for the 0.89. I'm getting close, 0.88, 0.8907, and I'm looking to see if I can find anything closer. 0.8925 is a little further away. So it appears, right, that the closest I can get to 0.89 is this value where the z-score is 1.23. Right, so just looking at the table, I have found that my z-score is equal to 1.23. So now I can put that in the z-score formula, and I know mu and I know sigma, so I can do some work. Okay, so let me pop out of that. Back to our PowerPoint, getting rid of these stray marks. Okay. And so now it's time to jump into our notebook. Okay, so going here, again, we have a lot of information. Also notice here that we have the SAT distribution is a normal distribution with an average of 1,000 and a standard deviation of 200. We have the ACT distribution, which we've been talking about, and we have the normal distribution for IQ scores. Traditionally, that was average human intelligence is 100 with a standard deviation of 15. Okay, so our example one, right, we calculate the z-score, right? Z equals 29 minus 21 divided by 5, right? And that gives us the z-score. Hang on just a second. Oh, I'm sorry. I have to actually print out the z-score, right? There is the z-score. And then, like the slide said, we can use this p-norm of 1.6, and that will give us this exact p-value, this percentile, right? And we just in the table got 0.9452. It turns out there's more decimal place accuracy that R can provide for us. So that's just redoing the first example we already did. And sorry, let me, right, this should probably go down here so I can delete that. All right. But what I want to do is I want to open up a couple of spots, right? Why? Because to do this 89th, the p-value of 0.89, I need to do Q-norm. And you remember we looked it up and we found that we thought it was about 1.23. Again, it's close to 0.123, but notice P-norm takes a standardized score and tells me the percentile. Q-norm takes a percentile, and notice that the percentile has to be delivered in percent, right? So we might say the 89th percentile, but we have to put that value in as a decimal 0.89. Okay, and that takes the 89th percentile and it calculates a z-score. Okay, well, let's actually save that. let's call it Z star. Well, I don't know. The star is multiplication. Let's call it, I don't know, Z sub 1 equals Q norm. And why do I want that Z sub 1? Well, because I'm going to actually put that in my z-score formula, right? Z sub 1 equals the mean, excuse me, the score that I'm trying to solve for, right? Minus the mean, which is 21, and that's going to be divided by the standard deviation of 5. Okay, and that's not quite what I want, right? I want to solve that for x, right? Because I'm going to be able to substitute in z1. I've actually created this variable z1, so it'll go right in there. So I want to solve this for x. Okay, let me see what I'm doing. So I'm going to do 5 times z sub 1, right? I'm going to multiply through by 5. Okay, so that equation now has been multiplied through on both sides by 5. Okay, and then I want to add 21 to both sides, right? So I'm going to have 5 times z sub 1 equals x, and I'm sorry, I have to add 21 to this side, plus 2, 1. Sorry, I'm trying to do algebra in the field here, but I believe you can see the algebra that I'm doing, right? I'm just taking the z-score formula, and I know z sub 1. So the point is to solve for x. I'd multiply through by 5, and then I add 21 to both sides. And now what I'm going to do is I'm going to switch sides, right? I'm going to calculate x. So let me do that. Let me just switch this. And I know what x is equal to. X is equal to all of this, right? The 5 times z1. Okay. And what am I going to do up here? Let me go ahead and just hashtag comment these. Why? Well, it was the correct algebra, but it's just going to confuse things. I know what z is equal to. Z1 is equal to. This is the correct evaluation when we solve the equation, and cha-ching. Now we know what? We know that Molly's score, I believe that was the name, was about 27 on the ACT. Now I know that it's 27.13264, right? But you score integer values on the ACT, right? So I'm saying that that's about a 27 on the ACT. So if Molly scores in the 89th percentile, right, then I can do a little algebra. I can use Q norm, right, to get the z-score. I can use the z-score formula to solve for x, and then I can evaluate x. Okay, so that's how the process goes. Let's see what other examples we have. If we knew that Dolly scored 87th percentile on the ACT, what was her score? Okay, so let's do let's do z sub d for Dolly. So her standardized score is going to be Q norm 0.87. Okay. And then what? Oh, it's the same thing. X is equal to, right? We've already solved this equation, right? So I take the denominator, it's basically the standard deviation times the z-score plus 21. And then we can evaluate x and see that, oh, so now it looks like the 87th percentile is a 26 or a 27. It's close to the 89th percentile 27 score. So this is the exact raw score. And again, ACT scores are integer values. So there's going to be a little bit of inaccuracy here, but we're going to have to round or do something to say what the ACT score is. All right. So for example 3, calculate the z-score in percentile for someone who scored a 1270 on the ACT. Okay. So let's do z sub s because it's an SAT score, right? And what are we doing? We have a score of 1270. And the spaces don't matter. Students have asked me this in the past. Hey, why do you put spaces in? Well, I put spaces in because I'm in my 50s and my eyes don't work as well as maybe yours do when you're in your 20s, right? And R is going to ignore those spaces, right? And so as I'm creating this formula, right, the score of 1270 minus the mean of 1,000 divided by the standard deviation of 200, I just see it better, right, if I have those spaces in there. You can type it without the spaces if you like. So the standardized score, the z-score, relating to that 1270 is 1.35. That means this score is 1.35 standard deviations above average. Okay? And and then how do I take this and convert it to a percentile? Right, I just do p norm, percentile for the normal distribution, cha-ching. So this score, this 1270, is a 91st percentile score, as you can see, 0.91. Okay. Example 4, find the 95th percentile SAT score. Okay, so now we're going to go to Q norm, 0.95. And that is, yeah, I don't know. Call it Z sub 2 for the moment, right? That's the Z score. We've gone from a percentile, 95th percentile, to a Z score, right? And remember, our Z score formula is, X minus the mean divided by the standard deviation, and I'm putting that somewhat in not mathematical symbols, putting it in words. Why? Because sorry, that's a Z. Why? Because I'm solving for this. I'm going to solve for X, which means that on the left-hand side, I'm going to multiply through by the standard deviation. Okay, so if I'm calculating this X value, right, this raw score, right, then what am I going to do? I'm going to multiply through by the standard deviation times the mean, sorry, times the z-score, sorry, put in the z2, right? And then I'm going to add the average, add the average of 1,000. Okay. And I need to actually have the X down here so that it shows me that, oh, hey, I scored a 1330. Now, I see that it's 1328.9707, but you know what I'm saying. These SAT scores are rounded to the nearest tens. You can make a 1300, a 1310, a 1320, a 1330, but you can't make a 1328.9. So we have two things, right? We have the exact raw score, right? But we're going to round that up to 1330, let's say, because that score is about 1330 on the ACT. Okay, so if you earn a 31 on the ACT, that's Joanna's score. Oh, wait, Sally scores a 31 on the ACT while Joanna scores a 1380, who did better relative to the test she took. Okay, so how about a Z-score for Sally? So Z sub S is going to equal, now she's on the SAT, right? I mean on the ACT, so I have 31 minus 21. And remember, if you need to scroll back up and look at these, averages and standard deviations, the average is 21, the standard deviation is 5. So I have 31 minus 21 divided by 5, and then print out Z sub S. And what about Z sub J for Joanna? Well, she's taking the SAT, so she's got a 1380 minus 1,000 divided by 200. And let's print out Z sub J. Okay, and so what do we see? We see that in terms of standardized scores, Sally's standardized score is 2 standard deviations above average, and Joanna's is still a great score at 1.9 standard deviations above average. A 1380 on the SAT is excellent, but the standardized score is slightly higher for Sally. Okay, and again, if you want to look at percentiles, right, I can do the P norm. Right, I can do P norm of Z sub S, and she's 97th percentile, and I can do P norm for Z sub j, right? And my goodness, you know, the difference is out here, 0.977 versus 0.971. We're out to the thousandths digits, 6 thousandths apart, roughly. Clearly, these are two exceptional scores, and they're very, very close in their relative strength, right? But if you had to answer the question, who did better, it's a slight, tiny difference. But you'd have to go with Sally's score because it's a higher standardized score, and it's an ever so much slightly higher standard deviation. All right, so we can compare, this is important to realize that we can compare two scores from different distributions, the ACT and the SAT, as long as we know the population mean and standard deviation for both of those distributions, right? And then we can compare who did better relative to the specific test they took. Okay, what is the 80th percentile IQ score? Okay, so we want to use Q norm of the 0.8. I'll do 0.80. Right. So how about Z sub Q? Equals Q norm, and then Z sub Q. Cha-ching, and then what am I doing? Well, okay, so Z equals, right, X minus the mean divided by the standard deviation. Need some parentheses in there. Right, that's what I know to be factual, but what's that going to do is I solve for X. I have to multiply through by the standard deviation, which in this case is 15, right? 15 times Z sub Q, right? Plus the average, which is 100, okay? And so the 80th percentile IQ score is about 112, 113. Now, IQ scores are generally given as integers as well. So, you know, we're a little bit, if we round this, we're at 113, but I would say that, yeah, it corresponds to an IQ score of roughly 112, 113. That's the 80th percentile. Okay, so what have we learned? Well, this is all the math that we do on standardized tests, right? We have a bell-shaped distribution for the scores. We take z-scores or standardized scores to convert those, and based on the z-scores, we can calculate percentiles for the whole test, right? And this is how we place people in terms of how strong their college application score is on the ACT or the SAT, or for standardized scores, you know, in K-12 schools, it lets us know percentile-wise how that student is doing compared to other students in his or her grade level across the nation. Okay. And then we'll use these ideas to develop statistical tests.